We now have a look at the first step of the content-tree algorithm, namely how to compute a regular edge labeling from a properly triangulated planar graph in linear time. For that, we need a new tool, the so-called refined canonical order. This is very similar to the canonical order that we already know, but there is one extra condition. So let's say we have a P2P graph G, then we want to find a labeling of the vertices from 1 to n, where the south vertex is the first, the west vertex is the second, and the north vertex is the last, such that for every k between 4 and n, we have the following properties. The subgraph gk-1 that's induced by the first k-1 vertices is biconnected. So we have already processed a biconnected graph. The boundary of this also contains the edge vs, vw. So the edge v1, v2 as we had it in the canonical ordering definition. If we look at the next vertex vk, then it lies in the exterior face, and its neighbors in this subgraph forms a subinterval of this contour, of this path between vw and vs, and it has at least 2 elements. Up to here it's the same as the canonical order, but now we also have some condition on what is left. So if k is at most k-2, then we have at least 2 neighbors in the rest g without gk-1. So there are at least 2 neighbors here. Let's have a look at an example. We have this graph, the first edge must be between vs and vw, so the next vertex has to be this one here. For the algorithm, we assume that there is a dummy edge between vs and vn, so that the graph is completely triangulated. Now for the next vertex, we must have a subinterval here as neighbor and at least 2 neighbors in what is left. So if we choose this as number 4, then this is the red graph. We have 2 neighbors here, so we can pick it. If we choose this as number 5, this is the red graph, what is left, we have 2 neighbors, so we can pick it. And then we can continue picking vertices that have this property, and as you see, the blue part keeps on getting larger, and the red part keeps on getting smaller. And it is not that hard to prove that you can always find such a vertex. This is again by going backwards, making sure you have no chords, and then you get it almost automatically. Now we have a canonical order. And from this refined canonical order, we want to compute a regular edge labeling. First, we want to have a look at the directions. So let's have a look at the situation. We have the vertex vk, we have our graph gk-1 here, and we have the graph g without gk-1 up here. The directions are very simple. Every edge we will orient from the smaller index to the larger index. So all the edges here are directed to vk, all the edges here are directed away from vk. But for the colors, it's a bit more involved. So we will first add a few definitions. vk has some neighbors here on the contour. The important ones for us are the leftmost one and the rightmost one. This is the left point, vt1, and this is the right point, vtl. There's another important one, which is the so-called base edge. So all these neighbors here have some index, and we want to take the vertex with the lowest index. And this describes the base edge of vk. So everybody else here has a higher index than ta. Now let's have a look at the outgoing edges. Again, there are 2 important ones, which is the leftmost one and the rightmost one. And that's also how we color those. So this first one between vk and vk1 is the left edge, and the rightmost one between vk and vko is the right edge. Now for this vertex we have colored 3 edges: the base edge, the left edge, and the right edge. In the end, this coloring that we get here from the base edges, the left edges, and the right edges should give us a regular edge labeling. That means that if we look at every vertex, color its base edge green, its left edge blue, and its right edge red, then every edge shall get exactly one color. First, we want to show that no edge gets two colors. So a left edge or a right edge cannot be a base edge. By definition, an edge cannot be a left edge and a right edge at the same time, because there are always at least two neighbors. This is where this part comes into play. If we have only one neighbor in the remaining graph, then the left and the right edge are the same, and we don't get a regular edge labeling. So let's assume for a contradiction that this blue edge here is also a base edge. If it is a base edge, it must be the base edge of VK1, because it's incoming here. We have a triangulation, so we must also have this edge from VT1 to VK1. It must be directed upwards, because this has index at most k-1, and this has index at least k+1. But, of course, this also has a smaller index than VK, because it lies in gk-1. That means that this one cannot be the base edge, because the base edge is defined by the vertex with the smallest index. And now we have a contradiction. So this blue edge cannot also be green, and symmetrically this red one also cannot be green. Now we show that every edge is either a left or a right or a base edge. From lemma 1 we already get the exclusive OR, but we still have to show that every edge gets a color. So let's have a look at all the incoming edges of VK. We want to show that all these edges get a color. And then we have this lemma. So we have our base edge here. We first want to look at all the edges to the left. Let's have a look at this one here. Then VTA is the right point of this vertex. Why is that the case? We chose VTA in a way that it has the smallest index. So the edge must be outgoing from here to here. And now this edge here is outgoing, and if we follow in circular order we get the first incoming edge. So this is the right point, because it's the rightmost incoming edge. And with a similar argument we can continue from here. Every vertex here is the right point of the next one in this order. So our vertex VTI has at least two higher numbered neighbors. That comes from the refined canonical ordering. One of those is VK. This one is not it, because it already has an outgoing edge from here by induction. So that means the other one has to be this one. So we must have a direction from here to here. And now again, this has an outgoing edge here. This is the first incoming edge in circular order, so this is the right point. And with the same argument we can go to the right and say that this is a left point of this, is a left point of this, and so on. Okay, so we have all the right points and left points here. And now look at all these edges. First, let's have a look at the left ones here. They must be right edges, because if we look at this vertex here, this is the right point, this is the first incoming edge. So if we continue, this is the first outgoing edge. So this is the rightmost outgoing edge here. We still have outgoing edges here. This could also go down here, but there cannot be another one there. So this is the rightmost outgoing edge of this vertex, which means it's a right edge, and we color it red. And the same way we get all these edges are red. And symmetrically, if we go to the right, then all these edges are left edges. All those are the first outgoing edge in clockwise order. So for every vertex, if we look at the incoming edges, we first have a bunch of right edges, then one base edge, and then a bunch of left edges. Alright, so we have a proper coloring. Every edge has a direction and one of three colors. The thing is, for a regular edge labeling, we only want two colors. We only want blue and red. So let's try to get rid of the green color. How can we do that? Let's again have a look at this vertex VK. We first have right edges, base edges, and left edges. This edge here should become either red or blue. And most of the time it doesn't even matter which color we give it. Except in the case that this is the leftmost edge or the rightmost edge. So if the base edge is here, then we color it red because we want at least one red color here. And if it is here, then we color it blue because we want at least one blue color. Remember, in the regular edge labeling, we want at least one outgoing and one incoming blue, and at least one outgoing and incoming red. If we would color this red here, then we would not have a blue incoming edge. But in this case, it does not matter. So now every edge has a direction and a color, which gives us two trees, the red tree and the blue tree. And we will now show that this is a regular edge labeling. So let's have a look at VK. We already know that for the incoming edges, we first have only red and then only blue. But what about the outgoing edges? We know that the left edge is a blue and the right edge is a red by definition. But we still have to figure out what about those in the middle. But note that all these in the middle here, they cannot have an incoming edges from something down here because they are stuck between these edges. So VK is the smallest index vertex that has an edge to these vertices. So these are the base edges of all these vertices here. Now we have a triangulation, so we must have all these edges. But what about the direction? We will pick the largest index among all these neighbors, which is our KD. Now all these edges must be directed in this way, from VK1 to VKD and also from VKO to VKD. And to prove that this is the case, this is exactly the same proof as we had before for the one with the smallest index in what lies below. We can apply exactly the same arguments here. So we have all these directions. But now look at all these guys. Look at this one here. It has an outgoing edge and then an incoming. That means that this edge here is the rightmost incoming edge. And now have a look at this. In every case, the rightmost incoming edge is colored blue. So this is a blue edge. What about this? Well, it has an incoming edge here, it has an incoming edge here, and then an outgoing. So this is the leftmost incoming edge. If we look here, in every case, the leftmost incoming edge is colored red. So this is the red edge. And for the one in the middle, we don't know, but it doesn't matter. It can be blue, it can be red. In either case, we have first only blue edges and then only red ones. So for this vertex here, we first have outgoing blue, then outgoing red, then incoming blue, and then incoming red. And that's exactly the condition we want for the regular edge labeling. And that means that we have found a regular edge labeling from a refined canonical order.